This video will take a little bit of time to discuss how to appropriately justify within an optimization problem. So I've got a few other videos where I've actually solved optimization problems. This video's focus is mainly going to be on how to provide that justification at the conclusion of one of these. So I've got an optimization problem that I did here. So we've got a three-sided fence built next to a straight section of river. It's going to be the fourth side of a rectangular region. We've got 96 feet of fencing available. Find the maximum enclosed area and the dimensions of the corresponding enclosure. So I drew myself a diagram. I'm going to have to build two sides that are the same length and then one side that is potentially a different length to complete my rectangle. The area is what I'm trying to maximize, so I have an area formula that comes together pretty quickly based on the variables I've labeled over here. Now this area formula does depend on two variables, so I used other requirements within the problem, 96 feet of fencing available, to figure out how to replace the y in this equation. So 96 equals 2x plus y, subtracting 2x from both sides, and then substituting 96 minus 2x in place of the y gives me an area function. Now, once your quantity that you're trying to optimize depends on a single variable, you're going to want to ask yourself a question. Is there a range of values that my variable has to sit within? And in this case, we are restricted by the amount of fencing that we have access to. I can make x 0 and use all 96 feet of fencing to build the side that's labeled as y, or I can build the two x's with all 96 feet of fencing and have the maximum value for x be 48. Now it should be pretty obvious if I use all the fencing to build the one y, or if I use all of the fencing to build the two x's, I'm not going to get the maximum enclosed area. But here's the benefit to having this interval. The conclusion that we'll discuss here momentarily is able to be developed with the Extreme Value Theorem, and we'll talk more about what that means in a few minutes. So I've got this range of values that x has to fall within. My maximum value for my area is going to be either at one of these endpoints or at a critical number within the interval. So I can take the derivative of my area function, set that area derivative equal to 0, solve for x. So the only critical number for my area function is x equals 24. Here's the benefit to having a closed interval. This area function is continuous. X has to come from this closed interval. The Extreme Value Theorem ensures that you're guaranteed to get both a maximum and a minimum for your function, and in this case it's this area function right here. And the maximum and minimum have to be either at the endpoints of the interval, 0 or 48, or at the critical number within it. So what I did is I evaluated my area function, so this area function right across this line here, at 0, at the critical number 24, at 48. The biggest of those results is my maximum. So in this case, my maximum area is 1,152 square feet. I attain that if I let x be 24. I get the y by plugging 24 in for this x. 96 minus 2 times 24 gives me the y of 48. When you have a closed interval that your variable from your function has to fall within, you can use the Extreme Value Theorem as your justification. Again, continuous function on a closed interval gets both a max and a min, happens either at the endpoints of the interval or a critical number within it. Here's the tricky thing about optimization problems. Not all optimization situations allow for this. So in this next problem, what we have is we have a can that we're going to design that's going to hold 24 ounces rather than 12. So what we want to do as we design this can is we want to minimize the amount of aluminum or the amount of material used to make it. So what should the dimensions of the cylinder, the dimensions of the can, be? I do have this little conversion factor here that we're going to need to use to get everything into cubic inches from ounces. What I have here is I have the can deconstructed. I've got the top, I've got the bottom, which are both going to be congruent circles. The cylindrical shell, if you cut the shell and roll it out flat, it is a rectangle. The dimension you see here on that cylinder is the height of the can, the height of the cylinder, and the dimension across the bottom is going to be the circumference around the top and bottom or around the sides of the cylinder. So the material necessary to make this is basically a surface area calculation for the cylinder, 2 pi RH for the surface area of the sides, and then pi r squared for both the top and bottom, and we have 2 of those. So here's my materials equation. Now from here, same sort of strategy as the previous problem. This depends on both the radius and the height of the cylinder. I would prefer if it depended on one or the other. So you'll notice what I did here. I did a quick conversion with this factor here to get from 24 ounces into the appropriate number of cubic inches. And I set that number of cubic inches equal to the volume of the cylinder, so pi r squared h. I solved that for h, so divided 43.321 by pi r squared. And I substituted that in place of the h that's here. I was able to do some simplifying after that happened. I could cancel these pi's. I could cancel this r with one of those r's. If I then multiply the 2 and the 43.321 together, I get this coefficient. And if I move that r across the fraction bar with a negative exponent and not touch the top and bottom portion of the surface area calculation, here's my materials function. This materials function depends only on r. Like in the last problem, we now want to ask ourselves, okay, now that this depends on a single variable, is there a range of values that r has to fall within? In this case, I have to satisfy this volume requirement. If I don't satisfy this volume requirement, I'm not building a cylinder, a can, that holds 24 ounces. So I have to satisfy this. Should be pretty obvious. I cannot let r equal 0, because if I let r equal 0, the volume of the can is 0. I cannot let h equal 0. If I let h equal 0, the volume of the can is 0. If you look at this range of values that r has to fall within, it does not include the endpoints. R has to be positive. I could design a can with a very, very, very tiny radius and a huge height that holds 43.321 cubic inches of liquid. Alternatively, I could design a can with a huge radius and a tiny, tiny, minuscule height that still holds 43.321 cubic inches of liquid. Now, those types of cans that I just described, they're not feasible, but there's no theoretical range of values that r has to sit within that includes endpoints here. We should expect a radius somewhere between 0 and 10, I would assume, just based on the volume of this can. But there's no theoretical restriction that requires r be within 2 fixed endpoints. Just has to be positive. So on the next screen, we'll talk about the justification, how we have to do things a little bit differently than in the prior problem. I'm going to go with the same procedure, though. I am going to take my derivative of my equation I'm trying to, in this case, minimize. I'm trying to minimize the amount of material. So I take the derivative of m with respect to r. So I've got a power rule being used there. Got another power rule being used there. Now you see here I've said I'm setting dm dr equal to 0. And the solution I get for that is 1.903. I'll show you where I got that. I did break out the calculator for it. This is a graph of dm dr. And the location where that graph is equal to 0 is 1.903. Now, because I can't rely on the extreme value theorem here, my endpoints for the interval that r has to fall within were not included. What I'm going to have to do is I'm going to have to use a slightly different justifying step. So I build a sign chart here. I know that r has to be positive, so r has to go from 0 onward to infinity. And I know the only time that the derivative of material equation with respect to r is equal to 0 is at this 1.903 value. Now if you look, this is a graph of dm dr. This graph is negative to the left of 1.903. This graph is positive to the right. What does that mean? Well, that means that the amount of material necessary to build this can is going to decrease as r ranges from 0 to 1.903, and then the amount of material to build this can is going to increase as r moves past 1.903. I've said verbally exactly what you heard me say over the last few seconds across these first 2 bullet points, If if the material necessary to build the can decreases from an R of 0 to an R of 1.903, but then it increases from a radius of 1.903 onward to infinity, I know my minimum amount of material to construct the can is going to occur at 1.903. I did plug that back into my volume requirement to figure out the corresponding height for that can. So here are the dimensions. Both of those would be in inches. Again, the justification in an optimization problem is going to vary. It's entirely dependent on whether or not you have an open interval for the variable in the formula you're trying to optimize, or if you have a closed interval. If you have a closed interval, you can rely on the extreme value theorem. If you have an open interval, have to do things a little bit differently, use a sign chart, and then verbalize that logic that you're applying to the sign chart.